Okay, let's continue. Now we're checking how does the amount of salt in the tank change. Well, we don't have any chemical reactions. There's nothing happening to the salt in terms of reactive in something else and disappearing or appearing. The mechanism for changing is either that you bring more salt and pour it in, or you're taking it out. So we are going to look at the problem a little bit more general than pure water coming in. If it was salty water coming in, we would need the rate of water coming in, and we need also the concentration of the salt that is coming in. So if instead of pure water we had salty water, say 0.1 pound per gallon, we will multiply that 0.1 pound per gallon with 2 gallons per minute to figure out how many pounds of salt come in at every minute. So we have two components. One is concentration of the incoming times the volumetric rate of water coming in. That's going to be another rate of water coming in. That's how you gain salt. And then we have salt leaving, so we need the concentration of water leaving, let's call it C out, and then volumetric rate at which it is leaving, which is 2 gallons per minute. So let me just write R out. So again, salt either coming in or leaving, we have to take account of both of them. The amount coming in is the concentration of incoming fluid times the rate at which it's pouring in, and the rate at which it's leaving is the concentration of leaving stream times the rate at which we are pumping the water out. Now in this problem, it so happens concentration coming in is 0. Rate at which the water is coming in is 2 gallons per minute. So overall, there is no salt coming in anyway. Rate at which the water is leaving the tank is just 2 gallons per minute. The crucial issue is what is the concentration of the salt that is leaving. That's the most crucial issue. Again, I invite you to pause and think about this and try your hand at figuring out what is the concentration. So how do you define concentration? Concentration, so for example, at the beginning, what's the concentration? At the beginning, we have 20 pounds in 200 gallons. So at the beginning, it's 20 over 200. That's the concentration. That's how many pounds you have per so many gallons. So the concentration is 0.1. But of course, the concentration is dropping because you're diluting this tank with pure water. So at the very beginning, yes, correct, it's 0.1, but as time passes by, it is changing. And what is it? Well, that's what we are after. We don't know. So concentration is the amount of whatever substance you have divided by the volume of the tank. Well, the amount we don't know. We were trying to figure it out. So we just leave it as A of T is how much salt is in the tank. Volume, well, in this case, it so happens the problem is that easy. Volume at time T is same volume that it was at the beginning, because 2 gallons per minute coming in, 2 gallons per minute is leaving. Volume doesn't change. Thankfully, all that is happening is the amount is changing. Volume is 200. So the concentration at time T is going to be the amount at time T divided by the volume at time T, which happens to be 200. And then the rate at which we are forcing it out, pumping the water out, is 2 gallons per minute. And then we have to subtract this thing from the other one. So in this simple problem, the first component was 0, and we end up with dAdt. Customarily, we drop this t. We know that it's a function of t. And this 2 and this 200 simplify each other, and I get a over 100. So the differential equation that I have is the following. dA over dt is minus a over 100. And remember our promise that all the differential equations that we are looking at here is of the following type. Derivative if some multiple of the function itself and perhaps some additional number. So in this simple case, we have dAdt is minus a over 100, and of course we said the second component that was easy. A0 was the amount of salt at the beginning is just 20. Next problem is very similar. Suppose a large mixing tank has 100 gallons of water in it and has 50 pounds of salt. Another brine solution is pumped into the tank at the rate of 3 gallons per minute, and when the solution is well stirred, it is then pumped out at the rate of 2 gallons per minute. So here we have a tank here. Some brine solution is coming in. Originally this thing has 100 gallons of water in it, and there is 50 pounds of, so A0 is 50 pounds. Volume at the beginning is 100 gallons. Okay, what we are doing is that we are pumping in at the rate of 3 gallons per minute, and then we are pumping out at the rate of 2 gallons per minute. This is leaving at 2 gallons per minute. So what's going to happen if 3 comes in and 2 leaves? It means we are filling up this tank, and at some point there is going to be an overflow. So there's a time to overflow. Just keep that in the back of our mind. And then says if the concentration of the solution entering is 4 pounds per gallon, this thing is 4 pounds per gallon. What it's asking us is to write a differential equation. So we want to write the differential equation, the harder part. What is dAdt? A0 is easy. This A0 is just, A0 was, this is 50 pounds. We said amount of salt is amount coming in minus the amount going out. Amount that is coming in is the concentration of incoming times the rate of incoming. And the amount that is leaving is the concentration of the solution that's being pumped out times the rate at which it's being pumped out. Okay, concentration coming in is easy. It's just given straight out. It's 4 pounds per gallon is coming in. Rate at this coming in, that's also just given to us, and is a fixed number, is 3 gallons per minute. So if you multiply them, you get 12 pound per minute. 12 pound per minute is just coming in. It's a lot of salt coming in. Minus rate going out, concentration going out. These two will require a little bit of work. Rate going out, no problem. It's 2 gallons per minute. So we are setting the pump to take 2 gallons per minute out. What about concentration? What is the concentration? of liquids that is being taken out. So concentration is the amount divided by volume. You have to remember at the specific time, at a given time, what is that? Well, the amount we don't know. That's what we are trying to find out. It could be a mistake to say 50 because stuff is being pouring in, stuff is leaving out. So we don't know what A is. How about the volume? So A, the numerator just stays as A. Volume, originally there was 100 gallons in it. We are pouring in 3, taking out 2. So volume at time t starts with the volume at the beginning. This is the original volume. And then we have the rate that is coming in minus the rate that is taken out. 3 comes in, 2 leaves. So every minute we have 1 gallons added. That's per minute. If you wait t minutes, it's going to be t. So it's 100. This was 3. This was 2. Becomes 100 plus t. So the volume is 100 plus t. So we have to write it just like that. A over 100 plus t. To clean it up and make it look like mathematical stuff without units next to it. 3 times 4 is 12 minus 2a divided by 100 plus t. So we deviated from our promise that everything is going to be that simple. Well, it's not always that simple. That is, sometimes a and b could become functions of time, or other things can happen. The problem can become gradually more and more complicated. If your amount that is coming in is a variable in time, or if you play with this pump and change the rate at which you're pumping out and so on, the problem becomes gradually quite complicated. Okay, next problem that we have in mind here, so we did the mixing problem. How about draining problem? Draining problem has to do with just letting a tank drain on its own. That is, just you're using gravity to drain it. All these problems, we had a pump. The pump was dictating how much water is leaving. Now we just make a hole in the tank or in the bucket, and we let the water come out, and the question is, well, what's going to happen? How fast does the tank empty? Okay, you might have seen it in your first physics class, or perhaps in high school you did a experiment in the lab or something. Take a container and make a hole somewhere in it. So there is a hole somewhere, typically, well, hole at the very bottom. You let the water come out. So you have water here. Due to water pressure and gravity, water is going to pour out. Now, at what speed would the water run out? Basic physics, or if you have done it in an experiment, is that depending on how high the water level is, so let's call this thing h, the speed of the water that is coming out, let's call the velocity of water, is a square root of 2 times constant of gravity times the height of the water at that moment. So this is the speed of water leaving tank under gravity. So we are not pumping it under gravity. And G is the gravitational constant, typically given to you as 32 feet per second square is the gravitational constant. You might be wondering, wow, where did that formula come from? Well, that is given to us, but in case you're curious as to where it comes from, why there is a square root there, and what does it mean, and so on, remember from your basic physics. So this is a side topic. I just mentioned it for those of you who are curious. If element of the water is up here and it has mass m, then its potential is mgh. Compared to this level, its potential is mgh. When it drops and falls out, that potential energy turns into kinetic energy. Kinetic energy is what? 1/2 mv squared. So just think about a stone that is falling. Its mass is m, its potential is mgh. After it falls h unit, its speed has become v squared. So this has turned into kinetic energy. Well, now cancel the m's, multiply by 2, 2gh becomes v squared, and when you take square root you get 2gh. So that's where the formula comes from. Now in these problems, in attempt to make it a little bit more realistic, you see a factor of c. It's supposed to take into account that there is some friction. We are losing some of our energy at the hole or in the water or something. So velocity coming out is some constant c times 2gh. So c is some experimental constant. It is less than 1 because it signifies that we are losing energy, and water coming out is not quite as fast as it should be because we have lost some energy. Okay, this is the velocity. Now, how much water actually coming out? Well, how much water coming out depends on the size of the hole. Bigger the hole is, the more water is going to come out. So if you have a hole and water is going through it at a velocity v, then the amount of water that goes through the hole is normal velocity times the area of the hole. So area times normal velocity is the amount of water that leaves. Well, the water that's leaving is leaving at the velocity that's given by this formula. Area, your book is writing at a sub h. I'm afraid that you're going to think that h has something to do with the height. No, it's unfortunate notation. The book is just referring to area of the hole. So a sub h is the area of the hole. So I just don't put the h there. A times velocity, we said c radical 2gh. So this is amount of water leaving the tank when height is h. Well, this water should be coming from somewhere. That is the amount of water lost from top of the tank. So what's the amount that is lost? That's going to be the area of the tank itself. So the amount of water that's lost is the area of the water up here times loss in the height. Now I notice I have perhaps no option but just to follow what the book recommending. This is area of the hole, so we don't confuse things. This is area of the hole here, down here, and this is area of the tank at the very top. I guess the textbook call it AW for the area of the water up there. So This is the amount of water leaving the tank. This has to come from up here, and what is up here is the area times the height will be the volume of the water there, and the change of the height in the unit of time times the area is going to be how much volume we are losing from the very top of the tank. These two have to be equal to each other. So what we do is that we set AWDH we set it equal to this, except that notice that this H we are losing height, and therefore the HDT will be negative. So for that reason we are going to have minus A sub H times C radical 2GH. So if we want to have a differential equation, we'll have dH dt, that's H was the height of water, T is time, we have ratio of the hole at the bottom to water surface at the very top times some constant times radical 2GH. So to make this look less crowded, and look at the mathematical aspect of it, is dH dt. We have all these constants here. Will be some constant, let's call it alpha, and what we have is square root of h. So all of these things we put aside is some constant. The essence of this differential equation is dH dt is minus some number times square root of h. Your textbook probably wants you to write this one because there's no alpha there. So this is the differential equation. How are we going to solve it? Well, we are going to see that in the next lecture, how we attack this kind of problem. But what the problem was asking was what's the differential equation for h? dH dt is going to be equal to some expression, and this is the expression that we have. Some specific numbers are given. G is given 32. Radius of the hole is given as 9 inches, so it's not a small hole at all, whatever it is. So we go ahead and then we say, well, area of the hole is pi times its radius, so it's going to be pi times 9. Let's see, was it? This is at 9 inches. 9 inches. So we have to make a correction. Radius was 9 inches, but since everything else is in feet, we better convert this thing to 912. So that's going to be 3/4, of course. So let me make a correction here. So area is going to be pi times 3/4 squared. What else do we need? We need the area of the tank itself. Area of the tank. What's the area of the tank? Am I missing something? But the size of the tank is not given, so I'm going to leave it as AW. So AW is just AW. C is also not given. G is given as 32. So some stuff given, some of them are just left out. dH dt, so let's write it out without, but that's fine. So pi times 3/4 squared, so that's going to be 9/16. AW is just AW. C is just C. G is 32. H is, well, just H. And this 2 times 32, 64 comes out, 8. This becomes minus 9 pi 8 on 16 gives me 2AWC radical H. Of course, H at time 0 was in the picture is 10, but we are not asked for that. So we worked it out. We got some simplified expression, and that is the differential equation for this draining phenomena. Again, a bit different from the kind of differential equation we saw for finance and such, but it's in the same ballpark. The derivative of h is some simple function of h, and that's what we are after. Here is a similar problem. Pretty much everything similar to the previous one, so maybe I leave that out. You guys go ahead and work this thing, and it's the same formula. It's the same formula regardless of what shape you got. So let's go after Mr. Einstein. He is falling. He is falling. So we are dealing with, we came to some free falls with perhaps some air drag and additional components to the problem. So here we have our friend Einstein is falling. God forbid. For high speed, okay, for high speed motion through air, such as the skydiver shown in the figure below, we never knew Einstein used to do skydiving, but let's assume falling before the parachute is opened, air resistance is close to a power of instantaneous velocity. So what's the issue here? We have the issue of air resistance. Let's see, what do we know about air resistance? As a kid, you probably did stick your hand out of the window and notice that the air is pushing on your hand. The faster the car goes, the higher the amount of force on your hand that keeps pushing your hand back. So that's air resistance. How big is that force? That is a lifetime effort to figure out what that force is. So people who study aerodynamics and such, like, I think they try to come up with shapes where this amount of air resistance will be low. So it's an area of research. Here we make the simplifying assumption. Air resistance in some problem, we see that it's proportional to how fast you're going. In that case, we say, well, it's proportional to velocity. Since it is opposing the velocity, it's going to be negative of that, and there's going to be some constant. In this one, it says, well, Einstein is very brave. He's jumping and not opening the parachute yet, and if you are going fast, so this one probably for slow speed might be good. For a fast drop, it could be minus some constant times velocity squared. Okay, so when velocity is very significant, especially at high speeds, velocity squared is going to determine the force. Now in your textbook here, the constants are sometimes they are shown with a positive constant, sometimes negative. In your physics books, engineering books, if a constant is negative, it's always explicitly showing its negative sign. So here, just read your text, make sure you are doing what the textbook is asking you to do. So air resistance is supposed to be a power of instantaneous velocity v of t. Determine a differential equation for the velocity v of a falling object of mass m if air resistance is proportional to square Assume the downward direction is positive. Use k larger than 0 for constant of proportionality, g larger than 0 for acceleration to gravity, and v for velocity itself. So it's telling us take downward direction as positive. Why is that significant? Well, if we want to write Newton's law, Einstein falling according to Newton's law. Newton's law says F is equal to ma. Who is a? Is acceleration. Acceleration derivative of velocity. What is m? M is the mass, and we are assuming that the mass of Mr. Einstein is a constant. What is the force? Well, force, there are two forces. One is that he is falling and a force of gravity is pulling him down, and that force is mg. So we have a force of mg is weight, is pulling him down, and due to his fast velocity, there is air drag on him that pushes back on him, and that one is kv squared. So the force made out of two components, there is a mg, he is falling, and then there is a kv squared, that is the air resistance on him. Well, F is supposed to be ma, so this is supposed to be ma. Well, what is a? So let's write ma. A is dv dt is equal to mg minus kv squared. I divide by m, so I make the problem straightforward about v. M divides to this one, and k over m is going to be here minus v squared. So this is my differential equation. Again, a little bit different from what we were promising at the beginning, but is in the same ballpark of differential equations. Okay, so I guess, so what did we learn? We had introduction to modeling, various problems in finance, biology, chemistry, mechanics, radioactive substances, heat distribution, light distribution, falling, and so on. Tie in various forms of differential equations, more or less of this type. So in the future sections, we are going to look at these topics in much more detail and actually solve the equations. Some of them are going to take substantially more time than the others. The more complicated the right-hand side is, the more time we are going to spend on the algebra of making it work. But the true message here is that the rate can be connected to the value of the function itself. We can use the laws of science to write the differential equation and then use mathematics to solve it. Okay, until next time, good luck and God bless.